Hi everyone, my name is Mehreen Chaudhary. I'm a graduate research assistant at the University of Texas at El Paso. Today I'm going to present to you my study on the optimization of a pressurized oxy-coal combustor. This is a project I developed for one of my classes and I would like to share it with all of you. So this is the outline that we are going to follow for our presentation. We'll start with the motivation and so on. So the main motivation of this research comes from electrical energy. So a major source of electrical energy is coal, as you can see from the energy scenario that in the United States, up to this year, 28% of the energy is produced from coal, and it is decreasing, it is declining to 17% by 2050. That's what is predicted. However, it is here to stay. Coal energy has been producing electricity for centuries and it is going to be here for the next 100 years or so. However, coal produces a lot of greenhouse gas emissions, and when coal burns with air, it produces NOx and SOx, which are very harmful for the environment. So, another alternative to uh, reducing the greenhouse gas emissions is burning coal with only oxygen. This eliminates the nitrogen and sulfur parts. We are left with only carbon dioxide and water vapor. This water vapor can be easily condensed and thus the carbon dioxide can be captured. A lot of research is being done into carbon capture units, but that is a whole different thing. So for this study, we will be developing combustor and optimizing the combustor design for this new technology to produce clean coal energy. So the benefit would be that we will burn coal to produce electricity, however, it just won't hurt our environment. So, as I was saying, a lot of research is being done in the sector, and Zabian et al. Said that in pressurization is the key to efficiency, and in this research field, there are three main cycles. These are um, stage pressurized oxy-combustion, thermo-integrated power system, and ENEL. ENEL is a patented design, a layout for this cycle. All of these cycles use pressurized combustion systems. However, there is a gap in literature because no clear designs are presented for these combustion processes. And that is from where we get our motivation. We want to develop a combustor which can sustain the high pressures and high temperature needs of oxy-coal combustion. Thus, the main goal of this project is to optimize a combustor design for operation in an oxy-coal environment, and uh, to achieve that objective, we have some sub tasks that we must follow. So first of all, we will have to do a thermal and structure analysis. We will investigate if cooling is required, and we'll investigate if it can sustain up to 10 megapascals of pressures. If it can sustain all of those, we will try to optimize our design to reduce the weight, and on the basis of all our analysis, we want to provide some design recommendations for future use. Thus, we will have a final design and the final recommendations for future researchers. So the flow of our design and of our research would be, we'll start with thermal analysis, we'll go to structural analysis, we'll do optimizations, and finally we'll have some design recommendations. So this is our entire oxy-coal combustor. As you can see, we have some parts. Uh, First, we have our power head. Our coal feed comes to our power head, and it is the coal burner. And then we have our main body, then secondary attachment, and lastly, we have our exhaust system. Now, all of these different parts are attached with flanges and gaskets. And on the main body, we have four ports for our sensory and optical ports. So if you see the design, the main action, the main combustion process is happening in our main body and our secondary attachment. The exhaust system and our power head do not see much fluctuations in terms of pressures or temperatures. So our study focuses on our main body and secondary attachment. We have taken these small parts because we want to take a closer look into these sections and determine if our combustor is sustainable to high temperatures and pressure. So this is a geometry for our design. First, we start with the entire geometry. Now, I have drawn this in ANSYS because I've drawn this in ANSYS, and then we take a plane of symmetry through this axis, and again another plane of symmetry through this axis. Thus, we finally have a quarter of the um, combustor. It is a cylindrical combustor, so it fits into a beautiful pie shape, and this will represent our values and results for the entire combustor. So the entire combustor is 80 inches in height, and it is 18 inches in outer diameter and 11 inches in inner diameter. That means that the wall thickness is 3.5 inches on either sides. Now, as I was telling that we have taken 1/4 symmetry, so we have symmetry along these two planes. For the boundary conditions, we have derived them um, using our design and using our objectives. We have applied um, frictionless supports on the um, symmetry planes, and we have applied displacement on the outer wall. For the inner wall, we have applied varying pressures. So as you can see from this table, we have applied an increase in pressures in an interval of 30 seconds. So we start from 0 seconds and we go to highest of 300 seconds, and we have a pressure fluctuations till 10 megapascals. Here is a closer look at our boundary conditions. As you can see, for our displacement, the body is free to move in. So the body is free to move in x and z directions, and the movement in y is restricted. As you can see again, it is the frictional supports, and the pressure is applied normally on the inner wall of the cylinder. For the thermal analysis, we have applied very complex boundary conditions. Now, these were very hard to find, so we went back to literature and we found the heat flux. We applied the heat flux on inner walls of the upper cylinder, and we applied convection on the lower wall and on the outer wall of the cylinder. So you can see that we have convection of ambient air on the outer wall, which is at 25 degrees Celsius. Now on the inner wall, we have a recirculation of hot flue gases. So we have applied convection on the inner walls. Now these conditions were derived from literature and using the NASA CEA to calculate our adiabatic flame temperatures. Now for the heat flux, we have applied it only on the upper cylinder because it is what sees the on the upper cylinder because it is what sees the heat generation, and on the lower cylinder there is only this convection. So for the setup, we did some mesh optimization processing. We have started with adaptive method, which was the default one, and then I applied proximity and curvature because the body has a lot of curves. Then I refined it, the mesh to be medium and then fine, and then I applied multi-zones. And then finally, I started applying mesh sizing. Now, I applied from a default 30 to up to 5. As you can see, after 9, it's the von Mises stress kind of started becoming constant, and we have chosen the mesh sizing of 8, as you can see from the graph, that after this the values are kind of parallel and they're kind of stable. So we chose a mesh sizing, default mesh sizing of 8 millimeters for our mesh. This is a closer look at our mesh, and you can see all the its properties are also listed on the tables. And for this, we have done multi-zone meshing because, as again, there are lots of different parts, and we have also done mesh sizing. So now let's come to the main section, the results. To obtain our results, we have done transient thermal analysis and transient structural analysis. Now these two analyses are separate, they're not coupled. Now I have done them separately because I wanted to see that if we have our maximum temperatures and what is the maximum duration that we can run our tests. And also from the structural one, we want to see what is the maximum stress and what is the maximum deformation. Definitely, these two results had to be, and this analysis had to be transient because it is a very dynamic process, and we wanted to see the changes in different ratios and different parameters after 300 seconds. This is the result for our transient structural analysis. Now I'm showing you the video. It is auto scale, so it's exaggerating it a lot, but we do see a quite increase in the stress. Now the stress concentrations are near the near the window. So the maximum stress is 58 megapascals, which is very low than compared to our allowable stress, which is around 450 megapascals. So our design is good to go. It can sustain pressures. It can it is very doing very well in terms of sustaining it. However, you can see that we have stress concentrations at the window. So we should do some steps to eliminate that. Maybe we could do some fillets at the at fillets or chamfers at the window, and definitely the inserts that will go into the window have to be of the same material, otherwise you'll have a mismatch because that window is already a place of deformation and already a place where stress is building up. And we can see on the uh, outer wall also there is some stress on the window. And the flanges, though there are some contact surfaces with the bolts, they do not see much stress. They are quite stable and they are quite stationary. They do not have we don't have to worry about them. Now comes the total deformations. For the total deformations, um, we can see that the deformation is maximum deformation is about 2 millimeters. However, this again is around the window, so we have to be really careful about designing the window. So we could eliminate the window at that would be the best option if we could do that. However, if we need the window for optical access, then we must be careful about stresses and deformations near the window. Here also another thing to notice is that there is small or almost no deformation in the outer walls, so we should be good with this amount of deformations for 300 seconds. These are not something that worries us. For the thermal simulations, we ran it also for 300 seconds. This was also a transient simulation, and you can see that from the ambient temperatures, the the maximum temperature that we got is around 750 degrees Celsius. Now this is very low in compared to our maximum allowable temperature, which is the melting point. However, this is only for 300 seconds, and so we must be careful for learning for using it for longer periods of time. Now, as I had applied only the heat flux in the upper cylinder, the maximum deformations are around the upper cylinder, and the lower cylinder sees very little deformation. These are again close-ups of our results. You can see that the outer wall has almost no change of temperatures. All the temperature changes within the inner cylinders and mostly within the first cylinder. So we will actually need cooling if we want to use it for longer periods of time, and we will need it in the upper cylinder. Now, depending on all of those two designs, we did run some optimization operations on it. So for optimizations, we chose our parameters to be our cylinder, uh, inner diameter, and our window diameter. And our objectives were to reduce the weight and to keep the stress less than 100 meg. So after running these optimizations, we ran quite a lot of design points. What we got is that we can change our inner diameter from 11-inch to 13-inch. That means we can reduce it by 2 inches, and the final diameter and a final cylinder wall width would be 1.5 inches. And our window diameter would be 5 inches instead of 4 inches. So this is the results that we got from our optimization. So we have seen that our combustor is safe for operations for 300 seconds. No cooling will uh, need to be incorporated for 300 seconds. However, we have seen that the maximum temperature is 750, right? So if we want to run it for longer periods of time, if we want to implement a factor of safety, we must implement cooling. We must implement some cooling channels on the upper cylinder, so that we can run it for longer periods of time and we can run it safely. And the combustor also does not fail at 100 megapascals. So in terms of pressures, it is completely safe. And depending on these two results, we have also done some optimizations, and the optimization came that we can reduce the wall thickness by 2 inches. And I would really love that, because having a heavier combustor always exposes to different problems of carrying it, of moving it in case of assembly, and a lot of other things. And the other optimization suggestion was to increase the window diameter. This, however, I differ with, because we have seen from our structural analysis that the windows are places of uh, maximum stress. So I would rather eliminate or decrease the window diameter if possible. So I would suggest that for future versions or future modifications, we need to incorporate cooling into our cylinder 1, and we must not increase our window diameters. Thus, the research goals of optimizations has been. So, in conclusions, we can say that our combustor can sustain temperatures and pressures for 300 seconds. It is safe to sustain 10 megapascals of pressures. We have also made some optimization recommendations. Therefore, the design of the oxy-coal combustor has been optimized on the basis of our analysis. Now, for future work, we could definitely do some couple simulations of temperatures and pressures. This would give us an idea of how it behaves interactively. We should uh, refine the meshes further using maybe a professional license, and we could see how the different components behave if we refine them further. And we can also perform some analysis on the power head and on the exhaust systems, which I would recommend to be static structural or static thermal, because they do not see much fluctuations. And depending on these results, future researchers can definitely start their work. So this would be like a base point for them to start their research. And I would really hope that someone would be reading this or seeing this and be benefited from our research. So these are the references that I have used throughout my presentations, and to find my boundary conditions and everything. So that's it from me. Thank you for being with me. Thank you for listening to my research. And please do reach out to me if you have any questions. Thank you.